Hi everyone. I hope you like this video. It's going to be a review of the practice that we had done in class. So nothing fancy, but I'll walk through every question and I'll try to describe what's going on in each one. And I hope it helps to clarify some misconceptions you might have had. Let's start with number one with this coin and a fair die being rolled. The one thing that you should know is that this is independent. You know, because flipping a coin and rolling a dice really have no effect on each other. They're very separate events, as opposed to grabbing marbles from a bag. Once you pick a marble, you've changed the game. You've changed how many marbles are in there, and you've also changed how many marbles of a certain color that you might want. So those are very dependent events. This is not the case at all. So anyway, the idea is a tree diagram. I've already done this once and then I just edited it out of your video because I'm really not good at spacing. So I'm going to do it top down like this. Okay, first we take the coin. You could have heads or tails. Then we take the dice. What are the possible outcomes for the die? Here they are. Now if you roll tails, since they are independent events, you have the same options for the dice. That's a tree diagram representing the total combinations of ways that you can roll a dice and flip a coin, and the total number is 6 and 6, which are 12. And I think that's what they're asking in the next question. Yes. That's what tree diagrams do for you. Now this topic here, this is called the counting principle. And it's pretty straightforward. The questions are generally like this. They give you some options like sandwich meats. You can choose from 3 meats, 2 cheeses, mayo or mustard, whole wheat or white bread. And you just set up a complete multiplication. Same here. This is a car. They're giving you a few color choices, sunroof choice, and so on. So you basically say, if there's 3 color choices and I'm configuring a car with every option, then I have 3 ways to choose a color. And you just simply multiply. With or without sunroof stands for 2. Manual or automatic stands for 2. And leather, fake leather, or cloth stands for 3. You multiply these out and you get 6 times 2 is 12 times 3 is 36. If you must have real leather and a sunroof. Okay, so you know what that's doing? That's taking this guy and saying, sorry, you have to be a sunroof, and there's only one way to choose that option. And then the other one with the real leather, that's going to be the last guy that I did over here. That's like saying you have no choice. So you multiply by 1. And now we go back with all of the other options and we say, okay, color, we're okay with that. No restrictions. Sunroof, there's only one choice we have. Transmission, we still have 2 choices. And the seats, we have no choice. We have to pick fake leather. And you multiply. 3 times 1 is 3, times 2 is 6, times 1 is 6. So you can see how by limiting your options, you limit the number of configurations you could possibly have. Last one, if you can't drive a car with a manual, okay, so we're getting rid of this. And you want a green or blue car, so we're getting rid of this. Oops, sorry. Oh, goodness. Bam, got you. Okay, how many possible ways can your car be configured? Well, how many colors do we have? Just 2. Still have 2 sunroof options. We're down to just 1 transmission and back to 3 on the leather. Multiply those. 2 times 2 is 4, times 1 is 4, times 3 is 12. That's the counting principle. This is interesting, especially these little C's right here. So for your notes, that little C stands for not. Okay, so probability of B union C. So, wow, maybe some more notes? Okay, that equals union. This means intersection. Now, this could also be the word and this could be the word or. This thing, this line, means having or given. Let's take a look. Okay, probability of B union C. So that would be like this. I want everything in B, so I'll color that all in. I also want everything in C. I'll color that in. And when you use the word or, only one item has to be true. So a common misconception is this. What if you're in the middle? Isn't that both C and B? So how could you be living in there and still be considered an or? Well, you can be, because to make an or statement true, which you might remember from geometry, only one has to be true. Both can be. That's cool. Consider yourself lucky. But only one property has to be true for an or statement to be true. So if you are living in the middle, you just happen to be both, but you satisfy this requirement. So where do we see this shaded? Right here in number 2. Okay, the probability of C. So the probability of C would be like this. Everybody in C. Even if they're overlapping the B right there, that's okay. If they're living there, they are definitely a C. They might also be a B, but that's okay. As long as they're a C, we are interested. So for question B, let's see where we can find a match. Bam, number 1. There you go. Okay, let's do another. Let's see if I can erase this nicely. Sort of. Cool. Intersect. B intersect C. That is going to be this, where they are both, where they are divergent, right, from that movie? So they have a little bit of C in them and a little bit of B in them. So that is 6, or VI. Here's that symbol again with having coupled with a little c, which means not. So here's what happens with this. If you get something like P of, or probability of, B given not C, that means this guy has to go first, followed by that. So let's figure this out. Let me erase and restart a nice little Venn diagram over here. Put this circle here, put this circle here. Okay, so who is not in C? That's huge. That's all of this, right? It's the outside box. Don't forget that that counts. And it's everyone in B. Okay, so that's first. Now, having selected, there's that word having selected that area in red, give me B. Okay, well, of all of that red area, the only reds that are hanging out in B are right here. We don't want to shoot into that other middle area. We're going to stay right there. Where does that picture look like? It is, boom, number 4, or IV. Letter E. This time we're going to union everything that's not in B and everything that's in C. So let's start with a fresh slate. Let's get rid of all this stuff. Okay, from scratch. I'll draw a new one. Okay. Now, probability of C union everything not in B. This guy goes first. So where is everyone not in B? That's the box for sure. And then this stuff right here. That's everyone not in B. But now let's join them with everybody in C. So look, this little guy starts to be included because we want to join them with everyone that's in C. So now we have all of this blue stuff all over the place. Where does that picture show up? V, or number 5. Now you could do process of elimination for this one, but let's talk about it. What's the probability of not being in B? Okay, this question is incorrect. It should be the probability of everyone not in C. Because you know that the outstanding solution is 3, which is this guy. And I think it was just a typo. So everybody not in C would be this picture. You shade in the box like this, and then everything not in C over here. So that includes the people in B, like that. And as you can see, that matches up to choice 3. So that's Venn diagrams and how to read them, and it's also a nice practice with the union, intersection, and that symbol that stands for having or given. 700 students at Newfield High School were surveyed. They have some favorite subjects. This is building a Venn diagram from scratch. Very important to remember that when you build them from scratch, don't start plugging in any numbers until you figure out the overlap or the intersection. For example, this will be, let's say, Spanish on the left, math on the right. Now, for Spanish, do we have a number? 68 were math, 48 liked Spanish. I don't want you to put 48 in there yet because your numbers will be too large. So 48%, let's call that 0.48. Let's see what else they gave us. So this guy's done. This number 68, that means students who like math. Okay, let's do that over here, 68. 26 liked Spanish, but not math. Okay, that we have to figure out where it goes, and that's going to help us to fill in the numbers. The 48 and the 68 do not belong inside these boxes or inside the circles. Okay, 26 liked Spanish, but not math. So inside this Spanish circle, but not crossing over into the math circle, we have 26%. That number you can put in. And it is from there that you will figure out the next the next 3 areas. You always have to be given one other thing to be able to complete your Venn diagram. We have it. It's this 26. So let's figure out who's in the middle. You would agree then that if 48 were Spanish, then we take away these 26 that are already hiding in the corner, running away from math, and we get 22. So that's how we know that 22 is in the middle. Now working the other way, you've got this 68 math, and 22% happen to also like Spanish. So let's see who are just the math-only people. Let's take away those people who are doubles, who like both, and we get 46. So that goes there. So what about this box? Who's in here? Who are the people who don't like math or Spanish? That's just like saying 1 minus, because 1 stands for 100%, 1 minus your 26 on the left, your 22 on the middle, and your 46 on the right. Gives you a total of 1 minus 0.94, which is 0.06, or just 6% do not like either subject. That's how you build a Venn diagram. You have to. You have to start with the numbers on the outside and look for some piece of information that tells you about a piece of these circles. Then you can fill in the rest. So what this question down here is asking is just, let's make this numbers. So we've got 700 students, right? So if we go back here, we fill in 2 circles, and we call this one, oh, those are horrible, sorry. You call these Spanish, these math, and these none. It's got to add up to 700. Okay, so it's as simple as saying 700 times 0.26, or what's 26% of 700? 182. That goes here. What is 22% of 700? That goes in the middle. And 46% of 700, 322. We add those up, and we'll figure out what goes in the box. You know, what is not included, because it does have to add up to 700. So we add these up. And we get, hang on one second, 658. Okay, so 700 minus 658. $42. Perfect. Pretty cool. Okay, now let's talk about some probabilities. What's the probability that the student did not take math or Spanish? Took neither. Who's not math and who's not Spanish? That's that guy. Oh, so probability, woohoo, 0.06. We don't even have to do the numbers. How many students didn't like either subject? Okay, that's when we have to go to numbers. So right here, 42, they were on the outside. What's the probability that a student liked math and Spanish? Well, let's take a look. 22, right? M intersect S would be 22. Let me put the decimal back on this answer also. Okay, and what is the probability that a student liked math or Spanish? Well, let's combine them. 26, 22, 46, which is 94. Oops, wrong way. And this is a great opportunity to revisit the formula for getting the same result, but knowing this: the probability of A or B. It is equal to the probability of A, we're going to add to the probability of B, but then as you saw in the Venn diagrams, you have to back out the duplicates. So that intersection piece, so we're going to subtract the probability of A intersect B. And if we go back to the Venn, the probability of Spanish was 48. Probability of math was 68. So we would say this: 0.48 plus 68. But let's not double count the people in the middle, because the people in the middle who were math and Spanish, well, they've already been counted in these math or Spanish percentages, and you'll still get the same 94. But I wanted to show you both ways, because this question by itself, without a Venn diagram, would have to be solved using the formula. But if you're lucky enough to have a Venn diagram, well then, why wouldn't you just go here and pick out the numbers? That would definitely be more straightforward. Okay? All right, great. So let's check out this set of data. There's 8 numbers. That's my sample size. And we want to know the probability that an even number is selected. Well, there's 1, 2, 3, 4, 5. There's 6 of them. So 6 out of 8 is your probability. Now, this probably meant to say, I don't know, simplest form. So that would be 3 over 4. The next question, prime number not selected. That's awesome because that's one of these crazy complement questions, which is 1 or 100% minus the probability that you do get prime. So how many prime numbers are there? Well, prime numbers are numbers greater than 1 that have only factors of 1 and the number itself. So right away, 1 is no good. He's no good. 2 is perfect because 2 is bigger than 1, right? And the only factors of 2 are 1 times itself. 4 is no good. 6, 6, 8, 10, 11. Haha, there's another one. So the probability of prime is 2 out of 8. So we do this. And if you use your calculator, you get 3 over 4. That's the probability of picking a number that's not prime. What's the probability of an odd or a prime? Now there's the formula that we're going to have to use from the last slide. You have to remember this. Probability of A or B is equal to the probability of A added to the probability of B, but let's get rid of the dupes. And in this case, you'll find that odd is 2 out of 8. Let's add that to prime, which is, that's funny, that's also 2 out of 8. But let's subtract any duplication. So is there such a thing as an odd prime number that we've already counted in our list? 1 is odd, but not prime, so we didn't double count that guy. 11, however, has been double counted because it is odd and prime at the same time. It's divergent. So let's get rid of that guy. That's 1 over 8. So the probability, therefore, is 3 out of 8. How about an odd number and a prime is selected at random? Well, that's the intersection. So the probability of odd intersect prime. Who would that be? Well, you got your odds are 1 and 11. Prime is 11. So there's the intersection. There's actually just 1. So there's only 1 out of 8. That's your probability. Okay, so 6 and 7, they meant to say, calculate the probabilities. And let's take a look. You flip a coin, then you roll a fair die. You want to find the probability of heads. Okay, so heads, is a half, 1 out of 2. An even number is going to be 3 out of 6. And if you want to do end, you multiply. So we'll take 1/2, we multiply it by 3/6, and you get 3 out of 12. Let's simplify this to be, there's a 1 out of 4 chance that when you flip a coin and roll a die, the coin will be heads and the die will be an even number. The last question says, same idea, let's just take the die twice. And we want the first roll to be a 5 and the second roll to be a 6. So the probability of 5, you'll know, is 1 over 6. Probability of 6 is also 1 out of 6. The word end tells me we must multiply. So 1/6 times 1/6 is 1 out of 36 chance. Number 8 is talking about a deck of cards. This is not your normal deck of cards. This is a deck of cards that might be presented to you on a Regents that's a little more generic, such that everyone understands what we're dealing with, because not everyone knows the componentry of a deck of cards, with the jacks and the aces and, do you pick the jokers or not? It gets a little crazy. So you pick a card at random. Are the events card shows a square, end card is red, disjoint? Disjoint is jumping. Okay, this means independent. That's just a really fancy way, like super fancy. The pinkies are out at this point. Independent. Perfect. So disjoint just means independent of each other, and I think you're pretty comfortable with what that means at this point, going through the video. So is there such a thing as a square red? So you look up here, you got squares, they're black. No more squares. You got some red cards here. None of them are squares. So the answer is no. No dupes. No, I shouldn't say that. Here's where it gets awesome. Because, check this out. Watch. Let's say probability of square intersect red equals, bam, the empty set. Isn't that cool? So if there's no overlap, that's a super fancy way to say no overlap, you are independent. What's the probability that the card will show a square or red? Okay, that's cake. That's probability of square plus probability of red minus the intersection of them. So is there any way that we can have a square red? And I think from the last question we know there is none. But that's okay. Probability of square is 10 out of 40. The sample set is 40, by the way. Sorry if I didn't say that. Probability of red would be 20 out of 40. And are there any red squares? No. So what do you get? You get 30 out of 40. And if you live east of the Mississippi, you know that this is the same as 3/4. Cool. And the events, card shows a 5 and the card is red. Are they disjoint? Is disjoint jumping or not? So we're going to say, let's see, 5. Where's our 5s? Oh God, they all have 5s. Every one of these has 5s in them, right? Because the numbers are 1 to 10. And are any of those that I just checked going to be red? Oh, absolutely. Look. And those are the red ones. So look where I checked twice. That means they have both properties. Okay. So are they disjoint? No. Because the probability of 5 and red is equal to 20 out of 40. And that's the answer right here. Cool. Now I think I just have to go back. I'm sure many of you are screaming right now saying, hey, you messed up. This was asking, are they disjoint? We're going to say yes. I apologize. Yes. Cool. This one is no. Sweet. Number 9. The spinner. Okay, so you can land on 1, 2, or 3. You're not going to land on the line, wise guys. I know what you're thinking. You're going to land on 1, 2, or 3. And you have an equal chance on landing on either of them, which is to say that the area of the 3, the area of the 2, and the area of the 1 are equal in size. So let's make a fraction of the probabilities of a 9. You spin 3 times. How many ways can you add up to 9? Well, there's really only one way. All 3 have to be 3s. What's the chances of that happening? That's a big old end. You have to roll a 3, and a 3, and a 3. So that's like this. Probability of your first one being a 3 times the probability of your second times the probability of your third. There is a 1 in 27 chance that you could spin 3 times on a spinner and your total of all 3 numbers would add up to 9. How about your 8? There's only one way to do that. 3, 3, 2. Or is there? Dun dun dun. This is a little tricky because what if you rolled a 2? I'm sorry, I always say roll, I apologize. What if you spun a 2? Then you'd have 2, 3, 3. And is there any other way we can arrange these spins to occur? Well, I think I could put the 2 in the middle. How about that? Cool. So there are 3 ways to spin 3 times and end up adding up to 8. Now, what's our sample set? That's the problem. What is our sample set? So the first spin can happen in 3 ways. The second spin can happen in 3 ways, and so can the third. So our sample set is 27, kind of like what we saw, in the question above. There's 3 ways to get what we want, so our probability is 3 over 27. And the last question, number 10. This is pretty cool. Talking about disjoint events and being independent, there's a way to prove it. And here's how. So if you want to show something's independent, having been given probabilities already, like not being able to know about a deck of cards or a dice and a coin, you use this formula. You say, hey, it is independent if the probability of A given B is the same as the probability of that first event, the probability of A. So in other words, the probability of A given B means B has already happened, right? Remember how this one was the first one to go? We did that in the previous examples. So B's already happened and we're happy. Now we got to get A out of the deal. Well, if that answer is just as simple as what it is to get A to begin with, then these are considered independent. It's that straightforward, and you just need to remember this formula and what these questions look like, because they'll always look like this. Probability of A given B is calculated as probability of A intersect B divided by probability of B. And the way I remember this is that this here looks like a fraction already in a fancy way. A divided by B. That's what that looks like to me. So look, put the B on the bottom. That's a way to remember who goes on the bottom. Okay? The second one always goes downtown. So let's see if this equals probability of A. So probability of A intersect B. That's multiplication. So probability of A intersect B over probability of B is like this. 2/5 times 1/5 divided by 1/5. Wouldn't you know it? Look at this. I don't even have to do this math. Bang, bang. We cross those out. Totally allowed to do that. Final answer, 2 over 5. What's the probability of A? 2 over 5. They match. This is independent. Now look at this question. They already give us PA of MB. And I know what some of you are thinking because I'm thinking it right now as I'm making this video and staring out my window at the traffic driving by. What the heck is going on? If P of A and B is 1/25th and they give us A and B here, if you multiply them together, you get like 2 over 20, not 1 over 25. So I get it if that's what you're asking right now. So let's look at it this way. We're trying to prove whether 2 events are independent or not. So these questions have just been made up for you to plug in the numbers and see for yourself. So we have to go with the notion that, okay, if they gave us this already, let's use that as the numerator. Because after all, that's the probability of A intersect B. Now we're going to divide that by the probability of B, which that's given to us as 1 over 4. Let's do that division and see what it comes out to. So right now my calculator, I'm doing that. I get 4 over 25. That is not A. So this is no. Okay, C. Kind of cool. We saved a ton of work because look, the probability of A given B is already given. That's like a double given. I love it. So 27 out of 50 is the final answer. However, is that equal to probability of A, which is 9 over 20? I think not. Cool. So for question D, I've got the probability of not A, someone's being very sneaky here, probability of B, and the probability of A and B. All right, how's that going to help us? I need to know this, right? So I need to know the probability of A intersect B. Well, this is beautiful because to figure out the probability of A, we're going to do 1 minus the probability of not A. And that gives us 1/4. Okay? I hope you see that. They gave us not A. We need A in our formula. So that's like taking the complement. Okay, cool. They gave us B, which is fantastic. And then they gave us P of A and B. How's that going to help us? Oh, ShamWow. That's the guy on top. Perfect. So let's put 3 over 40 on top, divided by probability of B, which is 3 over 10. Let's do this manual this time. Keep change flip. Let's multiply by the reciprocal. I think you'll agree that the 3's cancel. And the 10 and the 4 becomes a 4 in the bottom, so that's 1/4. Now, are you equal to the probability of A? Yes, you are. So this baby is independent. Nice, so we have a yes, we have a yes, so the yes get the corners on the top left and the bottom right, and we got the no's for these guys. So this is how you can prove independence if you're given the probabilities of events. Number 11, two-way tables. If they tell you that it's 1,000 two-way table, that means that the grand total of all totals is 1,000. That's all. And what do you do next? Well, we got to work our way through all the given numbers and fill them in as possible. So they're talking about a claim. Dogs were classified as large or small, and whether or not they passed an obedience test or not. So let's talk about some of these numbers. Okay, 45. What is that? The number of dogs involved in the classes that were large. Well, that's a total, isn't it? Large dogs adds up to 0.45. 60 passed the class, so that's a total of everyone passing the class, so we'll put 60 down here. Records indicate that 40% of the dogs in the class were small and passed the course. Okay, that's an intersection of passed and small. Passed and small. That's 40. That's all I'm given. Okay, so, what else can I fill in then? Let's look at the totals. I've got a 60 here, which is in this column that has a 40 in it. Okay, well then this has to be 20. This is completely empty, so we have to figure out another way to do this. It's like Sudoku, right? How about this way? This 1,000 is everybody, right? So if I'm using decimals, I'm not going to use this 1,000. I think I jumped the gun there. We're going to use 1.0 to represent 100% of all the dogs, which we just happen to know is 1,000. You can recall in an earlier question where we did Venn diagrams with percentages and then we put numbers in. That's the same thing here. So instead of using the numbers, let's use the percentages. 100%. So 60 plus 40 would give us the 100. Does that help us at all? Yeah, 20 plus what gives us 45? That would be 25. Beautiful. Now I can add these up. 25 plus something is 40. That would be 15. And now I can go this way and get 55. 45, 55 equals 1. Everything checks. This is awesome. Now let's do some probabilities. Probability that a dog selected at random passed the course. That's simple, right? I mean, it doesn't give us an end, it doesn't give us an or, and it doesn't give us a giving. It just says, what's the chance they passed? So that's 60. Well, what about if the dog selected was large? That comes first. What's the probability that the dog passed? That comes second. So what you're looking for is this: probability of passed having already been selected as large. Cool. So that's going to be this. It's going to be the probability of passed intersect large. Remember how it looks like a fraction where the large is on the bottom. That's how I remember it. Cool. So let's look for the intersection of P and L. Passed large, that's 20. Divide that by P of large, which is 45. In my calculator, that's Zanfini again. 0.44444444. Okay, any rounding? No rounding. Okay, so 0.44. What about a dog randomly selected from the dogs that completed the class? If the selected dog is a small dog, what's the probability that the dog passed the course? Okay, again, it's one of these guys here where first you got to get a small dog if you're lucky, and then wow, even if you're even luckier, they've also passed the course. So there's like two probabilities going on, so that looks like this. What's the probability of passed given small? I think you're getting used to the formula, so let's intersect passed and small and divide it by small. Let's go back. Where's past? Here we go. Past, small is 40, and then small is 55. So it's going to be 40, 55. In my calculator, I have 0.4 divided by 0.55. I get 0.72727272. That's actually pretty cool. Okay, so let's just say 72. Do you think a dog size matters when it comes to passing the course? So did size have an issue with passing? Well, in C, small dogs passing 72%. So if they were small, 72% of them passed. Whereas in B, if they were large, 44% of them passed. Absolutely. Small wins. Awesome. Okay, and do you think large dogs should get a discount? What a random question. Obviously, I didn't read this ahead of time. That's funny. No. And I have no explanation. All right, and the last one is a two-way table that's been given to us. It's already filled in, thank God. You're asked to determine if two events, a randomly selected student has asthma and a randomly selected student has a household member who smokes, are they independent? What probabilities could you calculate to answer this question? Well, remember what we did to prove independence is the probability of A given B the same as the probability of A? And if so, you would call those independent. Or disjoint is jumping. Okay. So let's see what we got. Probability of A given B. So I need to know this. Probability of A intersect B, and I'm going to divide that by the probability of B. So if I look at my table, I'm looking for the intersection of randomly selected student has asthma, and a randomly selected student has a household member who smokes. So the probability of randomly selected student who has a household member that smokes would be what comes first. So what's the chance of asthma having already picked a smoker? So my B is going to be having already picked a smoker. So where is smoker and asthma intersecting? This is smoker, right? Here's asthma. Okay, 113 out of 937. Divide that by smoke. 395 out of 397. Let's do that division in our calculator. Or we can do keep change flip, which I see as being pretty cool here. Because look what happens with the 937. They cross out, and you get 113 out of 395. So what's the probability of A? A is asthma. Probability of asthma. The probability that a student has asthma is 182 out of 937. So the probability of A, let's see if that simplifies to the same fraction. I'm just going in my calculator right now and I'm typing 182 divided by 937 and I get 0.194. And when I look at 113 and I divide that by 395, I get 0.28. No, they're not independent, which is scary if you think about what that means. Calculate the probabilities you described in part A. I just did. I don't know what that means. Oh, sorry. I think I went too far. So this question was saying, hey, like what probabilities could you use? And then the second one was saying, go ahead and do it. Well, we kind of already did. So yeah, these are not independent. Okay, so that I think, let me check. Nope, it's not the video, sorry. Ha! Almost. That was like the 5-minute early pass when people start leaving, you think class is over. It's not over yet, we have a few more minutes. Based on the probabilities you calculated, are these two events independent or not? We already talked about that. Is the probability that a random selected student who has asthma and who has a household member who smokes, is it the same or different from the probability that a randomly selected student who does not have asthma but does have a household member who smokes? Explain your answer. All right, well, we know the probability of the first part, right? Let's go back and check what it was for a student who has asthma and who has a household member who smokes. 113 out of 395. What's the first part? So let's go calculate this. Let's calculate a randomly selected student who does not have asthma, does have a household member who smokes. So what comes first? The asthma. So this is the probability of smoking household given the student does not have asthma. So let's figure out that. Okay, so we'll call this one A, we'll call this one B. So we need to find the intersection of them and then divide by B. So let's go back and look for smoke, no asthma, and then let's look for no asthma. So smoke, no asthma. So this is smoking, no asthma, 282 out of 937. Cool. Now, probability of not having asthma, 755 out of 937. And if you're getting used to these questions already, this will reduce to 282 over 937. So were they the same? No. This is not the same. Oh, sorry. Sorry. 282 out of 755. Sorry. Let me change that real quick. Are they the same? No, they are not. Okay, and if a student selected at random, what's the probability that the selected student has asthma if they've already indicated that they have a household member who smokes? So that's this. That's the probability of asthma given smoking household. That's what that word problem is standing for, right? So you select a student. They already tell you that they have smokers in the house. What's the probability they have asthma? So that's like saying, what's the probability of them having asthma if you've already picked them and they had smokers in the household? So I think we did that question back here. 113 out of 395 or 0.28. Okay, cool. I hope you liked the video. I hope it was helpful. I appreciate you watching them. And good luck on your quiz on Monday. Take care. Have a great weekend.